Hello everyone, my name is Camilla Kashner and I'm an organizer at the GDG Cloud Budapest community and I'll be your host today. Let me also introduce Zsigmond P. Tóth. He's head of Google Cloud Hungary at EPAM Systems and also the co-organizer of our community. He will be the moderator today. Hi.
Hello, everybody.
And here's also Balázs Molnár, cloud architect from Deutsche Telekom IT Solutions. He will be the one giving you exciting insights into the world of LLMs today. Hi, Balázs.
Hello, Camilla.
Thank both of you for joining us. What is this community about? At the GDG Cloud Budapest, we aim for bringing cloud professionals, especially GCP enthusiasts, together to learn from each other and share their professional experiences, all the how-tos and best practices for the newest cloud technologies. So if you want to be a part of this community, reaching almost 900 members, visit our meetup.com page where you will find all of our future events. Find the link in the chat or scan the QR code on the slide and click on the join button. And before we dive into today's topics, I'd like to take a moment to introduce the main partner of this event as well, Deutsche Telekom IT Solutions Hungary, DTITS for short. As the largest ICT employer in Hungary, DTITS plays an essential role in driving innovation and providing top-tier solutions to their international corporate customers in areas such as software development and system integration and operation. But beyond their business expertise, Deutsche Telekom IT Solutions has been a significant contributor to this community as well, consistently offering resources and speakers for our events, just like today. So we are very grateful for their support, which helps make events like this possible. Here you can see some of their GCP-related open positions. So if you're interested, scan these QR codes or screenshot the whole page and visit their career website. You will find the link in the chat as well. And that's it from my side. Thanks for the attention. Balázs, the stage is yours.
Thank you very much, Camilla. So yes, let me shortly introduce myself. I'm Balázs Molnár, and right now I'm working as a Google Cloud architect in the cloud professional services of Deutsche Telekom. But I'm quite new in Deutsche Telekom, and I've been working for more than 3 decades in different areas of software engineering and architectures. Since I have a long track record, I managed to see many technologies rising from nowhere. But when I first saw technologies like large language models, like ChatGPT or Gemini, it was a real shock for me too. And actually, I was really amazed by what these technologies could do. And my first thought would be, if I would be a small kid who would like to understand how the music box work, that I would like to understand what is the technology behind this model, what is the technology behind this magic. So this is the journey I would like to invite you for today, right? So we will have a quick look at the large language models, the history of the large language models, and we will try to open this magic box and see the gears and rods and pistons in that box, and find out that what major technologies are used under these magical models. Okay, so I would like to share my screen. I hope you see that right now. Okay, so at the first part of my presentation, I would like to introduce a little bit these technologies, which are in the background of large language models. And in the second part of my presentation, I would like to give you some practical view on how to use this technology in real life projects. And I would like to show you a few projects we are also working on. Definitely, if you are a black belt artificial intelligence expert, then you will hear nothing new. But actually, if you are just a technological savvy person who is really interested in what are the main technologies and what were the technological development and evolution of this large language model, I hope that you will get some sort of overview about these technologies. But let's start maybe with the history a little bit. So Imagine that actually these machine learning and artificial intelligence technologies are quite old. So the first technologies, what we are using now, the first neural networks, were developed right after the Second World War. So it's a Cold War technology, and there were already the theory of neural networks were already known. But at that time, we had very limited computing resources and very limited amount of digital information. And as you will see, you need a lot of these if you would like to use these artificial intelligence tool efficiently. And actually, from the large language model perspective, the next great evolutionary step was in 2001, when really a very important technology emerged. And this was called embedding or vectorization. This was really a technology which enabled us to understand the meaning of the words and represent the meaning of the words with numbers, right? And that was really a prerequisite of many language-oriented services like search, translation, and so on. But also it was very important from the large language model perspective as well. And then, of course, the next step would be the multitask learning, where we were able to create models which we can use for multiple purposes, generic models, not just models which were built for just a single purpose, like differentiating a picture of dogs and a cat, and the model could not do anything else. In 2008, we were able to create models which we were able to use for multiple purposes. The next big steps were in the development of the neural networks. So more neural networks appeared, which we will talk about that, what were the evolutionary steps of these neural networks. And in 2017, there was a very revolutionary model which was developed, which was called transformers. And that model, large language model, was able to create, with these models, we were able to create the first large pre-trained language models. And in this picture was generated by Google. So in this, we can see that this led to BERT in 2018, which was one of the first large language models, T5, GPT-3, where most of the people first met with this technology in 2020. And now we are in 2025, where we have got quite advanced models, a lot of different models trained for different purposes and priorities. We are able to consume text and streaming and videos and sound. So in the last 5 years, there was a huge development in these large language models. So actually, this is the quick history from technological perspective of the large language model. But let's go back a little bit to the basics. So I want to go back to the neural networks because if you want to understand the technology and sometimes the terms what we are using together with large language models, you need to have a certain understanding how these neural networks really work. And I would like to, rather showing you a lot of slides, I would like to use a very nice simulation tool. I hope you see it on my screen, right? A very nice simulation tool, which was developed by Google to demonstrate the capabilities of TensorFlow, which is one of the model development environments which are available, and it's a very popular environment. And this shows, it's a simulator tool which shows how neural networks learn, really. And actually what you can see here is a very basic neural network architecture, and which has a single task, right? So we give a few dots, a few dots in a space, right, based on an XY coordinate system. And we give some colors to these dots. And the model has to identify, based on the coordinate of the dots, that what should be the color of the dot, right? So here you can see a lot of blue dots in the middle, some orange dots at the outside part of the picture. And the model needs to understand what is the rule behind this. And if I try to train this model, the background color will show that the model quite quickly learned that all the dots which are outside this central circle should be orange and within the circle should be blue. Okay, so let's see how this thing works really. So what you can see here are neurons, right? What are neurons? So the neurons are, like in a human brain, the neurons are cells which are connected to each other. Here, neurons are functions, right? Very simple, relatively simple floating point operations. They are collecting some inputs on their input side, execute some activation function, right? You can see here a few basic activation functions which can be used, and they are producing, again, a floating point output, right? So these are the neurons. But what is interesting in this whole story is not really the neurons, but the connections between them. Likewise, in the human brain, these connections can be strong or these can be weak. And this is what is changing during the training process. So if you, what we are doing during the training process, we are collecting data sets. In other words, we are collecting epochs. These epochs are known inputs and known outputs. So in this case, coordinates, and the output will be color. And we collect a lot of these, and we feed the input values into one part, and we will be able to ask the model to generate an output. This process is called forward propagation process. And what it does is actually goes through the whole neural network, execute all the multiplications, execute the activation functions, and execute the weights, which are stored in a matrix, also called tensors, the output before it gets to the other neuron's input. And when we generate this single output, we are able to compare the generated output with the known output of the training set. And the difference between that will be the loss, right? So if there is a difference between what we calculated and what is the truth, then there is a loss. And taking this loss, we are able to adjust the weights of these connections, which are also called parameters, right? So let's see it again, what happens. So when I start the training, for example, this connection has a weight of 0.11. When I start the training and finish the training, I see that the loss was decreased to less than 1%, right? So it's a quite accurate prediction. And now the same weight will be 1.4 instead of 0.1. So this is, the backpropagation process itself is a quite magical mathematical operation. It's a quite complex one. You can find a lot of information how it works. But actually what you need to understand is that these connections are really representing the knowledge of the neural network. And these are the same as what we call parameters. Okay, so but let's give some additional more complicated task to this network. Now we have got a different training set, right? The orange dots are in different shape and the blue dots are in a different shape. Let's see how it can learn. So we give more and more information to this, but actually the accuracy of the whole environment is still quite high. We almost entered 1,000 samples, and we still have 30% of the outcome is still false, still not good. So this model simply is not intelligent enough to solve this problem. I've been trying for much longer, but I don't want to waste your time with it. So what we can do to improve the capabilities of this model, we can add additional intelligence to that, which means that intelligence in brackets, which means that we add more neurons to this environment. We are also able to change the activation function, right? So make some changes in the model, do some experiments by changing these parameters, and try to train again. At the beginning, there is not too much difference, right? But after a while, after 100 or 200 samples, the model starts to learn much faster, right? So it will be able, it is now 99% more accurate, right? So this is what happens when you would like to give a more complex task to this neural network, right? And what also happens is that the learning curve of this model is getting more complicated, and the resources what we need to train this network will be also more complicated. And that's why we need huge amount of computing power, because what you see on the screen is approximately 200 connections between the neurons. But for example, the large language models has several hundreds of billion connections. So you can imagine how much computing power would be needed to calculate all the steps of forward and back propagation. Fortunately, these operations can be executed parallelly from each other. And that's why NVIDIA is getting more and more rich in the AI world, because NVIDIA is producing GPUs and TPUs, tensor processing units, which are especially made for this kind of parallel operations, and which can be very nicely used for making forward and back propagation processes. Okay, so these are practically, you can find the link in my presentation, so you can play with this model. It helps you a lot how to operate and how do neural networks work. But let's move on. So we understand now, at a certain extent, that how these neural networks work. But how do we use them as a developer? So of course, what I showed you so far is only a simulation tool. If we would like to use it as a developer, we need to use some frameworks like TensorFlow. So TensorFlow is a library what we can use to build and train these kind of models. And if you are interested how a code like this looks like, you can see, for example, here a model which describes that, okay, describes these layers of the neural network. So we will have a dense layer with 100 neurons with a ReLU activation function, and then a 75, then a 50 neuron, and at the end we will have a single one with a sigmoid activation functions. So we can build these kind of models. We can use data sets. We need to create data sets, which the format is also defined in the specification of the TensorFlow. And we can execute trainings. So if you are interested in how the trainings work in real life, we are using, or data scientists are using, typically Jupyter notebooks for this. What is this Jupyter notebook? It's a special tool which is a combination of a terminal and a documentation tool. So you can have code segments in it, and you can have documentation segments in it. And the code segments can be executed because all these Jupyter notebooks are running on a virtual machine or on a container, right? But you can also read the explanation of this code, what is working. And for example, here you can see the training process, right? So you can see the epochs, the training sets which are placed into the model, and you can see that this loss. So what we have monitored in the previous simulation is decreasing. So this is for the loss was 45%, and they decreased down after 200 operations to 33%, right? So this is the tool what data scientists are actually using. Data scientists are called scientists because they are not programmers really, because this is not programming, this is experimenting. So what you are doing, you are changing something in the model, you are using a training set and hope that the model will produce the result what you want. But if it doesn't, then you need to change some parameters and execute the training again and again. And you will need to find a solution when the model will produce what you want to achieve, right? So this is how developers are building neural networks. But this is just the basics, right? We need to solve some additional problems when we get into large language models, or we would like to process text. One of the challenges what we have is that these neural networks, what you have seen, are working with numbers, floating point numbers to be more precise, right? And one of the challenges that we are working with text and language, right? So we need to somehow translate text into numbers, into floating point numbers. And that can be a challenge. Of course, we can use coding systems like ASCII or Unicode, but then we have to, if we have got a 1,000-page document, then we have to process each and every letter of that document with a neural network, which would be extremely expensive. And it is not really an efficient solution. So what the developers or the developers of these technologies found that they rather would like to work with tokens. Tokens are so-called linguistically meaningful units, the smallest units which are linguistically meaningful, right like a word, for example, right? And we put these words into a vocabulary, and the index of the vocabulary can be a number, which we can use in the large language models. The problem and the challenge with this approach is that not all the languages are the same. So languages like English don't like so much adding prefixes and postfixes to the letters. So practically you can transform any word into a token, right? Because it can be a very basic thing. But in other languages like Norwegian, Arabic, or Hungarian, for example, we are using a lot of prefixes, a lot of postfixes, which are fundamentally change the meaning of the word, and especially the meaning of the sentences, right? So there is a challenge that not all the languages are using the same type of tokens. And there is one interesting characteristics that, for example, if you see this text here, you can see that this text contains 468 characters and only generates 105 tokens. The same in Norwegian. If we translate this sentence to Norwegian, it will be about the same amount of characters, but 157 tokens, right? Almost 50% more. And if we are using Arabic, which is a completely different type of language, we need to use 286 tokens instead of 105. And let's check what happens if we try to do it, the same text in Hungarian. I'm going to use an online tokenizer. for doing this, which is from OpenAI platform. And I will copy the same text to the tool. Okay, well, not the same text, maybe. Yeah, I've lost that. But here you can use, it's a different text, sorry. It's English. Okay, sorry. This is the Hungarian text I want to paste. So this is the same text what was written in English here. So which required 105 tokens for English. And in Hungarian, we need 171. So we are more complex than Norwegian, but less complex than Arabic. And you can see that there are a few words like omikor, which can be a single token. But for example, there is another word called felébr, which it was waken up, right? It means, and it contains actually 3 tokens or even 4 tokens because it's assembled by different elements of the words. However, it is grammatically not really correct. So the way how this tokenization in Hungarian works, for example, is that they are analyzing thousands of documents, and the letters which are most commonly together are identified as tokens. So this is how we are tokenizing the words. So this is one technique what was required to translate tokens from languages or text to numbers which can be fed into neural networks. But still we have a problem. So even if we are generating tokens which are language specific and we don't need to analyze the characters one by one, these tokens will not represent the meaning of the words, right? And this is where the real technological breakthrough came here. It was around 2000 when the first embedding engines were created. And embedding set a new ambition. So we want to translate the words and the text into numbers, but we want the numbers to represent the meaning of the words as well, right? So not only just a serial number, an index in a vocabulary, but we would like them to represent somehow the meanings. And we would like to have similar words, have similar numbers, right? And we would like to have synonyms almost the same number as the other synonym, right? And how can we do that? So this embedding technology or vectorization technology works in a way that I would like to illustrate here. This is just an example, right? But imagine that there are a few words like queen, king, woman, girl, boy, and so on. And we have got 3 dimensions, right? We have got the age, the gender, and the royalty. And we know that, okay, queen and king are quite close to each other from royalty perspective because they are both part of the royal family, but they are quite far from each other from gender perspective because queen is a woman and king is a man. And of course, princess and queen are quite close to each other, both in the royalty and age, but both in gender and age, but in gender and royalty, but in age, they are different because princess is typically younger than queen, right? So what embedding is about is that it is generating not a single word, but multiple words. In real life, it's 500 to 4,000 dimensions is used, and each of the words can be placed into a place within that dimension, multidimensional space. And this multidimensional space will represent the meaning of the word. So if we would like to turn the word queen into numbers, we will not get a single number, but we will have 4,000 numbers, which will place the queen into the semantical space, right? So the next question would be that how to define these dimensions, right? So age, gender, royalties, just 3 dimensions, but definitely they are not enough to define all of our words. Actually, we could invite a lot of philosophers and linguistic professors into a room and start to debate about what these dimensions should be. But actually, it's not work like that. Probably it would not work like that. Actually, we don't need to know that what is the meaning of these dimensions. What we want to achieve is that if the words has similar meaning, then it should represent it by similar numbers. If it has a different meaning, then it should generate different numbers. So actually, what was a nice experience that the meaning of the words are really dependent on the context of where you can find these words. So, for example, if you are taking 1 million documents from the internet, the words which have similar meanings will be surrounded. You will experience that the words which have similar meanings are surrounded by the same words, right? So the context where these words appear in these 1 million documents are very similar to each other. So the synonyms will be surrounded by the same words in like the other synonyms, right? And based on this idea, what they did, they used a neural network and trained that neural network to predict the surrounding words from the center word, right? And then use, so if we go back to our neural network model, and instead of, so imagine that this neural network is predicting, so here we enter the central word, and it will produce somehow the surrounding words of the central word. And actually, they did not use the output of this neural network, but they used the parameters of this neural network. And they placed here 500 or 4,000 different neurons, and they used these parameters as the vectors, which are representing the meaning of the word. And this experiment has really worked, right? So the similar meaning words had similar parameters. And this is what is called embedding. Maybe if you cannot understand my explanation, it's not your fault, probably it's mine. But what you need to remember that embedding is something what is representing the meaning of the word or the meaning of the object. We're going to talk about that later. And it is a multidimensional space, right? And it's generated by an artificial intelligence tool. What is also interesting that if you are using other neural networks like, for example, image recognition networks and so on, you can also use these parameters to define the meaning of the picture, for example. So if you are using a neural network which is able to create a caption for the picture, so describe what you can see on the picture, then you can use the parameters of that neural network, the internal parameters, to create an embedding which will describe somehow the meaning of that picture, what is on that picture. Okay, and also it is possible, and there is an interesting possibility in this technology, that if you are using special language models which are able to process multiple languages, then when you are generating vectors for a word queen, it will be very similar to the vectors of the word királynő in Hungarian, right? So when you are using this, you will be able to say that királynő, which is a Hungarian word for queen, is very close in meaning to queen, which is an English word. So embeddings can be language independent, which is also a quite interesting possibility. Okay, But anyway, anyhow, we are generating somehow these vectors, which are representing the meaning. What can we use them for, right? So what we can use them for is, once we have created these 4,000 numbers, which are representing the meaning, we are able to find similar meaning words, similar meaning of pictures, similar meaning of text sequences as well. So what we need to do is we need to compare these vectors to each other. And if the distance between these four vectors are smaller than a certain amount, then this means that they are talking about the same meaning, right? So let's make some experiment just to show you how this works. There is a Finnish university who created this demo. You can find this link as well. And you can play with these embeddings, and maybe it helps you understand how it works. So if you put here a word like queen, it is able to, so it has got a dictionary, right? And it will be able to show you the nearest 10 words to queen. And you will find these like queens, princess, king, monarch, king, princesses, and so on. And you are able also to compare the distance between two words. Like, okay, so I say queen, what is the distance between queen and princess? Between 1 and -1. So the similarity is 0.70, so 70% same meaning. But if I enter here queen and computer, they are definitely not that similar. So only 4% similarity between queen and computer. I wonder what that similarity is. But anyhow, it says that it is only 4% similar. Okay, so this is how we can calculate, we can quantify the distance between the meaning of the words. And once we are able to do this, we are able to do a lot of things like search, for example. So this is how for Google search works. That, for example, you have got a lot of data, right? A lot of documents, and you are breaking it to parts. You are creating vectors, embeddings for those parts, right? You are storing these vectors together with the reference to that part in a vector database, right? It's a special database which has a special index, which is able to search within that, right? And when you would like to search in this database, you are taking a question, a search term. You also created an embedding with the same methodology and with the same function library this question, and you simply compare and calculate the distance between the question and the documents we have in the database. And you are able to pick the nearest neighbors. So this is, for example, Google search will be able to find you, based on your query, documents which are not even in the same language, because their vectors will be very similar. Or even if you do not mention the specific word in your question or in your query, it will, what is in the document, still, it will bring you up a few documents which are talking about the subject, what is in place. One of the nice tool which is using this is this so-called notebook LM. I don't know if you know this tool or not, but if you not, I would suggest you to take a look at that. What you can do this with Notebook LM is you are able to create notebooks, right? In that notebooks, you are able to put documents. The documents or links to websites or simply pasting some text. And if they are uploaded to this notebook, you will have a language model and you are able to ask questions about the document, right? So for example, have a question. This is a document about the Gemini 1.5 multimodal language model. And you are able to ask questions like, how many tokens Gemini 1.5 Pro can take in a prompt, right? You simply ask that question, right? And the tool will answer this question, right? So this is what we used in several, this is the capability what we used in several AI projects now, that is able to answer your question that up to 10 million tokens as a prompt. And what is interesting here is this small number index, which shows to the part of the text where this information is located. So this is using a vector database, right? So the vector database embedded all these chunks, created an embedding for the document, and it created the same embedding for your question, and the distance of this document and the question was very close to each other, and that's why it used here in the answer. Okay, so this is a very nice example how embedding works. And this was really a very important technology of the large language models, which had to be developed before we could proceed. Okay, so what is the next step, right? So we are now able to understand the meaning of the words, able to understand the meaning of the pictures. We are able to create neural networks which are able to learn. So how we can proceed? So actually what was needed is the development of the neural networks. So what I have shown you was a very simple neural network, and it is definitely not sufficient to perform the operations which are required for the large language models. So we needed more advanced neural networks, more advanced architecture of neural networks. So I would like to show you a quick history about this development. So the artificial neural network, the first instances of that was developed for the first implementations already happened in the 1960s. But these were quite limited. So we could recognize, we could differentiate a dog from a cat, or predict some stock prices or something like that. But it was quite unreliable, and it was quite limited. Then we introduced the deep neural networks when scientists realized that if we put more neurons into this model and create more complex architectures, do some transformations between the layers, then it will produce better results. This is also the time when the convolutional neural networks worked, which is used for image processing. So decreasing the resolution of the images, try to identify a few features on the images and train a neural networks which is able to recognize a dog or a cat on the picture based on the features they have. All of these elements contains a lot of transformation layers, a lot of neurons, a lot of data processing. But all these initial neural networks were really focusing on a single input. From a single input, it generated a single output, right? So they were not really able to manage streams of information like text, right? So we have words coming next to each other. And if we would like to translate, for example, one sentence to another language, then we need to understand the word which came 2 times before. So we need to also understand the series, the whole series, and not just the single word we are working on. And this is what the recurrent neural network really achieved, that it could have a stream input and a stream output, and the different elements, the first elements of the stream were able to influence the last element of the stream as well, in a certain extent, because that was one of the limitations of this network, that it was not able to remember for too long. So if you had a text with 1,000 words, it was not able to remember what was the first first word. And the way how it achieved is they are connected, the hidden layers of these neural networks, but I don't want to get into the details of this. You can have a lot of documents which describes how these models are really working. And then they invented a new model which was able to remember, differentiate the more important words from the less important words, and was able to remember for a while the most important words. Then they made some sort of optimizations because these neural networks became very, very complex, and it contains a lot of neurons and connections, and we had to make them simpler. And that's why the gated recurrent unit was developed, which doing the same thing as the LTSM, but in a simpler way. And then using these advanced neural networks, they started to develop specific models for processing languages. The first one was the encoder-decoder, which was first used in, for example, Google Translate, where we translated input sequences in one language to output sequences in other language, right? One of the problems with these models was that it was too much parameters. It required 50 million parameters just to predict a single word. And it was not able to handle changing orders of the word, because one sentence in a language and the order of words in a single language can be completely different in another one, right? And that's where the attention mechanism was invented in 2050, which was able to manage this word order differences in different languages, and was able to understand the similar format words, which has different meanings, like bank robber or river bank. In both cases, we are using bank as a word. But in this case, this is a financial institute. In this case, this is the part of the river. And this model was able to understand the differences between these. And then we arrived to transformers, which were able to understand the context as well. So for example, in a sentence like the animal did not cross the street because it is, I cannot read it, it's okay, because it was too tired. So the word it refers to the animal, right? So this model was able to understand also the context. And then we arrived to 2018 when the first large language model was invented. It used 110 to 340 million parameters, right? So quite a large one. And it was able to do something similar what the current language models are able to do. So they were able to answer questions, they were able to classify documents, they were able to compare documents and so on. And from 2019, we have got a large variety of large language models available. Each one has a little bit different architecture, a little bit different sizes, a different amount of parameters. And it could be used for different purposes. Some of them are very good in certain languages. Some of them are very good in other languages. Some of them can consume also images and sounds and pictures. Some of them don't. So we have got quite a big variety of large language models, which can be used for specific purposes. Okay, so this was the theory of large language models, but let's see how we can use them in the practical life, right? So what can we do with these language models in real life? So first of all, I would like to, because I'm working in Google projects now, I would like to show what Google's role is in this place, right? So actually, Google has done a lot in this area. So as you can see, Google was involved in development of several language processing models and a lot of other technologies. But as you could see at the beginning, what we need to train neural networks is a lot of data and a lot of computing power, right? And Google has both, right? So Google has the search engine, which contains, which can see a lot of information, digitalized information. It can get access to a lot of pictures, right? Together with the texts around them. So it has got a lot of data. It has got a lot of computing capacity they are operating Google Cloud, but also they are operating large systems like YouTube, like Google Search and the others. So it has got definitely a lot of computing capacity. And of course, they know the technology because they invented a large part of these technologies as well. So what we can do in Google Cloud, actually, we can of course, we can develop custom models, right? So if we have got the skills and if we understand how this works deeply, then we are able to train these neural networks. We are able to use TensorFlow, use Jupyter workbook, what we have seen, to develop these models. But we of course, we can use the Google Cloud for hosting these kind of codes. So we have got virtual machines and containers where we can assign resources which are required to run and train these models. But we don't have to do that. In reality, in real life, we are very rarely developing our own models. What we are doing is we are using the pre-trained models in most of the cases. And that is actually nothing different from using APIs. So these large language models has APIs, and we can use our programs written in Python, for example, which can access these APIs. And the same way as you are doing a chat with ChatGPT or Gemini, you are able to do a chat between your program and Gemini, and in case of Google, but probably ChatGPT has similar AIs as well. You can do tuning existing models with your own data set. So if you would like to use Gemini 1.5, but you would like to add some additional knowledge on top of what it has, you are able to create a separate instance of that, and you, with creating training data sets, you are able to add new information to this. And of course, there are some custom-based industry-specific solutions which are based on AI, like Document AI and Contact Center AI, and others as well. But let's have a look at this AI console, what we can use. And I will make some walkthroughs through these models. Okay, so you can see in the Vertex, under the Vertex AI. So if you go to the Google console, under the Vertex AI, you will see all the tools which are available in this topic. So in AI topic. And one of the most interesting parts to start is this dashboard, where you are able to access the different models. So for example, if you would like to generate image based on a prompt, you will find this in the model garden. Get into Imagine 3, which is a model which is able to generate pictures based on the prompt. And you are able to access it through a studio, right? So if you are entering here a command to generate a certain type of image, then it will generate the image for you. But this is just a console. Of course, you can do the same from code. And if you are interested in how you can do it from code, you can also get into the model and open a notebook. I will open it via myself here. Yeah, maybe. So for example, getting started with image generation. You will find a Jupyter notebook here, which explains you with samples and everything how to generate an image from your code, right? So this is something what you can tell. I do not have the time to explain every single part of this, but I would like to show you one interesting thing, which is a quite new capability of Google Gemini engine. And this is actually the new model capability, which helps you a lot if you would like to learn complex technologies like Vertex AI. So what you can do with the newest model, with the Gemini 2.0 Flash experimental model, is to share your screen, and you are able to discuss this with the large language model. So let me share my screen.
Okay. I understand that you said chip and then IYA. Is there anything else you'd like?
No, actually, I misunderstood this. So first, I would like to share my screen. Stop sharing. Okay, I would like to start a new stream. Share my screen. So now you hear the Gemini. Okay, can you tell me what do you see on the screen now?
Sure, I see the Google Cloud Platform Vertex AI Pipelines page. It looks like you've clicked on the View Details button for the LLM text generation evaluation pipeline, and now I can see a loading screen with a blue spinning circle in the middle of the page.
Okay, what is the element what I just highlighted now?
The element you just highlighted is the model name preprocessor node. It's a container type node, and based on the node info, it takes in location, model name, project, and service account strings as inputs.
Okay,
It
what does it mean container in this context?
In this context, container refers to a software component that packages up code and all its dependencies so that the application runs quickly and reliably from one computing environment to another.
Okay, thank you. So I think that you now understand the potential what is in this, right? So whatever you would like to use, but you can do it not only with the Google console. If you would like to use Photoshop or something else, it can help you in this as well. So I suggest you to visit this open aistudio.google.com, select the stream real time and start sharing session and start conversations about the details of this technology. Okay, so but I'm running out of time now. So I would like to talk a little bit more about the projects we have been done recently. So actually, we in T-Systems, we have developed several AI projects, and there are a few interesting ones. As you see, most of them are not very new, so they are using some old capabilities of AI, but still they are very useful for the companies we are talking about. For example, I would mention Mercedes-Benz low monitoring project. So the problem was for Mercedes that Mercedes is designing cars, and in every country they are delivering their cars in 136 or whatever amount of countries, and whatever they operate, so wherever they supply their cars, they have to meet the legislation of that country. And whenever the legislation changes, they has to get notified about that. So what we use AI for is that AI monitors the legislation changes in all of those countries with 136 languages. It translates them into English and notice if there is any change happened in the legislation which is relevant from car design perspective. So the project itself was, we were using the standard models, right, of Google Vertex AI. So the development work was mainly about transforming information and to the proper format and call the necessary APIs, what produces this result. Very similar project in UNIDO. This is a university. And the same applies, but we need to process a lot of documents, but not legislation, but internal policies. And a similar way how I use Notebook LM they would like to discuss or ask about the large language model about their own policies. There is a German city for road maintenance, which is an image computer vision project where garbage collection cars are continuously monitoring the roads. And if they detect some anomalies, like a tree is covering a traffic sign or something like that, they immediately create a database what can be used by the road maintenance company, and they can find action points that they need to cut off trees and so on, or cover bumps or something like that. But we also created an internal project like this video knowledge base system. So like this meetup, there are a lot of videos which are recorded in different languages all around the world. And we collect them into a central database, and you are able to search in that knowledge base based on the content of the videos and the subtitles of the videos, which are automatically generated. And you are able to search in these videos if you would like to. So these are the few real-life examples we have been working on in T-Systems. And all of them are based on Google Cloud and Google AI capabilities. So during these projects, you have got several options. How do you want to use the AI in your project? Of course, you are able to create new models, but as you can see, it's a quite complex task and it requires very special skills and deep understanding of these neural networks. So these large language models were developed with thousands of man-years, I would say. So it's not really realistic to develop something similar in the frames of a project. So, but if you would like to do something simple, this is also an option, what you can do. What is a more realistic option is to retrain an existing model. So take a large language model like Gemini, for example, and retrain it with some corporate data, and then it will be able to answer those questions which are in the corporate data as well. You will have a separate instance of this large language model, and it will be able to answer your question. But it requires, again, quite a lot of resources to retrain these very complex models, and it requires some infrastructure to run these models as well. So what is the most important and the most often used technique is the prompt engineering. And the prompt engineering is much more than just entering good queries to the large language model. So you are able to send queries or prompts to the large language model with from your code, and sometimes you are able to create multiple iterations between your code and the large language models. And you can use the large language models for generating commands which can be executed in different systems, or SQL queries which can query a database. You are able to put corporate data into the context, and it is also then the large language model will be able to answer based on the input what you have given. So one of the techniques which can be mentioned here is retrieval augmented generation. And the way how it works is actually, for example, a customer would like to know whether he paid his bills or not, right? Your customer. You take this enterprise prompt, and the large language model is instructed in a way that if the customer is asking about his information, then please generate an SQL query which will retrieve his information from an SQL database. And the large language model will generate an SQL query based on some examples what you have given to the large language model in the context, right? So you will have an SQL query which can be sent to a classical enterprise database, right? And retrieve the information which is interesting for the customer. Then you will get this information. You put that information into the prompt, right? Together with the question of the customer, and instruct the large language model that do not use the data from the internet, do use only the data from the context. And then the large language model will be able to answer the question of the customer based on the information what you have retrieved from the enterprise database, right? And this can be done with vector databases. This can be done with any kind of integration between your code and the different source systems. So large language models can be used as an application which can generate several interactions. So for a single enterprise prompt, you can generate several requests to a large language model. You can filter, change the response before you send it back to the customer, right? So this is a technique which is very often used when we are developing such projects. And what is the advantage of this technology is that you can use enterprise data without training large language models with enterprise data, because you are simply adding this enterprise data to the prompt, right? And the data will sit on your classical systems, and the large language model will be still able to respond based on that data. You can use much less data, doesn't need to be transferred into a proper format, which is required for training these models. And of course, there is a limitation how much information you are able to put into the prompt. So you need to write this code, which is executing this kind of RAG very carefully, because actually you cannot put the whole database into the context because it can produce only a limited size of the prompt. And there is another interesting challenge in the enterprise type of projects, and this is the reliability. So probably you heard a lot about hallucination, right? The model sometimes make huge mistakes. So artificial intelligence is inherited the humankind negative capabilities, not just the positive. So they are making mistakes, right? And actually what you need to do is somehow manage these kind of hallucinations. And there are a few techniques which you can use in prompt engineering to manage these hallucinations. One of that is called grounding. Some models, like the Gemini models, has its built-in capability of grounding. What it means that if you receive some answer from a large language model, then before you send it back to your end user, you are executing a fact check on that. So you are making a search to a vector database or to a simple website or a search engine and check if that answer can be found in reliable documents or not. And only those sentences or only those paragraphs will be sent back to the customer where you are able to find the reference in the reliable documents, which says the same thing, right? So likewise, we did it in Notebook LM. It's a reliable document, and if we are able to find the location where this information is, we treat that as a reliable information. Otherwise, we simply forget that paragraph, right, and that sentence. So this is grounding, and it can be quite useful when you would like to improve the reliability. But there are some other techniques, more advanced techniques like React, for example, where you are forming the prompt with multiple iterations with the large language model into a format which large language models understands better, right? So for example, if you would like, if you might say that please add the numbers together from this database, all the numbers together, it might produce a wrong result, right? Because of the hallucination. But if you break this task into parts and say that, okay, collect all the data in this document and create a formula from this, all the data, what needs to be executed, right? And this is the first step. And the second step, calculate this formula for me, right? Then this will produce a better result. And there are, this React has very special format. We do not have the time to get into the details, but you can search for it in the internet, which really improves the way how you ask questions from the large language model, and it reduces the probability of hallucination and the mistakes. Okay, we have got our last topic, which is the offline or online models. So what I showed you so far are all online models working in a managed environment. This is what you are using when you are talking to ChatGPT as well. So there is some infrastructure in the background where this model is running, and you don't need to take care of that infrastructure, right? It's managed by Google or managed by OpenAI. You are just using the API and you get the answer, and it doesn't matter if you are generating 1 million requests or just 2 requests. It is scalable. Of course, you pay more if you are generating more requests for it, but you don't need to take care about that problem. What you can do is that you can download these models to your own computer. There are some frameworks which can do this, like Ollama, and you can install these models into your computer, and you can run it there. And then the only thing what you need to pay for, there are some models which are free of charge. There are some paid models, but actually this will run on your own infrastructure. So all the data will be there. Only those people will get access to that who will get access to your infrastructure. But all the infrastructure needs to be managed by you. So you need to assign a quite large resources to this. So for an average language model, you would need a virtual machine which contains at least 70 gigabytes of memory with 200 gigabytes of storage. So it is, and with some GPUs or TPUs assigned to that. So you will, for using the large language models, you will need significant infrastructure which can be used. I'm asking my colleagues how much time do I have left? 3, 4, maybe I will just quickly try to show how this works, because I have done this in Google Cloud. So here I have an instance where there is a VM where I installed this model, and I could use commands like Ollama, and I can list different type of models here. So we are looking at a virtual machine, and you can see that we have got 3 models downloaded, and we are able to run one of these models. So I execute run Ollama, right, like a batch command. It will take for a while until it loads, but it's loaded already, so it's quite fast. And I can, of course, enter some statements, right, in the same way as I did with the online models. So, for example, can you write an SQL statement which selects all the names of the table called customers, right? I just simply add this, a simple one, and you can see that it started to respond, but it's a little bit smaller or slower than the online models, as you can see, right? But it generates this SQL statement. And also you can generate a poem with the style of Shakespeare, right? But it will, again, will be a little bit slow, right? So much slower than what we experienced with the online models. And of course, these are not the latest technologies and not the best models. But we can see that, for example, this model capabilities. So show info. It's a llama model. It has 8 billion parameters. It can process 8,000 tokens. It produces 4,000 embedding dimensions, right? Now you understand these terms. What does it mean, right? So actually, this is also something what you can do, but you need a quite big machine, and the performance of that quite big machine will be much more limited than the online ones. But it has got a different cost structure, so it has got a lot of advantages as well. Okay, so we arrived to the end of the presentation. I hope that I still not lost you. We have been looking at the basics, how neural network works. We understood how text can be converted to number, which can be consumed by neural networks. We also learned something about the evolution of these language models and the neural networks. And we have a brief look at how we can use these technologies in AI models. And I hope I managed to give you a few real life project examples, what you could see. So thank you very much for the attention so far. And I don't know if we have got any questions regarding this.
Okay, can you hear me?
Yes.
Then thank you very much for the presentation. Let's see the questions. We have collected a couple of them. So let's start with a rather simple but valid one. Does AI store information securely? What can we do to protect our sensitive data? Can we do anything at all?
Yeah, okay. It's a good question. So it depends, right? So AI does not store information in the same way as traditional systems does, right? So we do not find a file where all the information is located. Everything is located in these neural network parameters, right? So when we are training, the information is here. If you are able to understand what is it, then congratulations, right? Of course, if somebody has got access to this instance where what you have been trained with your own data, then he can ask questions and the answers will contain sensible information. But for example, with techniques like retrieval augmented generation, that is an advantage that you do not store the enterprise data in the large language model. Actually, you just give it to the large language model in the context, right? And immediately you send the context, a prompt to the large language model. It gives you the answer and immediately forgets everything, right? So it will be not retrained with your data, and it will not store your data. Of course, you need to protect the communication if in a classical way. So you need to do the same things with the large language models as you would do with a database, right? You need to protect the communication channels. You need to protect the temporary spaces where you are preparing your data, but then your data will be safe, right? In this technique. When you are retraining an existing environment, retraining an existing model, then you will have a separate instance, right? And that separate instance will be only accessible by you, right? Whether it will run in the cloud or in your own infrastructure, but that will be only accessed by you. Here, the risk is, of course, a little bit higher, but I think it's still quite secure. I hope I managed to answer the question.
More or less, yes, but let me just add a little addition to this question. So how does this work in case of existing large models like ChatGPT or Gemini? So, for example, if some of my personal information managed to get into the training data, and I would like to remove it, then is it possible to remove it? Because you can remove it from a website; it's very easy, but from a trained AI, it could be more tricky.
Yeah. So in case of ChatGPT, so what we need to separate is that you have got a web application where you put your questions in it, and you will see the list of questions right in front of you, what you have said before, right? And this is a web application which stores these questions. And if these questions contain sensible information, of course, this needs to be asked from ChatGPT to erase it, right? Because that previous history of discussion is stored there. And if the history contains sensible information, then of course you need to take care of that, and you need to delete it, and you need to read the data management conditions of ChatGPT. But what I just would like to repeat, that the fact that you are asking a question from a large language model which contains sensible information, it does not mean that the large language model will remember your question next time.
I'm not talking about when you are asking, but for example, when accidentally some of my personal information was published on the internet, for example, and that data is used as an input data for the training model.
Okay.
And someone asked that, what is the address of Zsigmond? That it turns out that it can provide my exact address.
Yeah. Yes. So if you have once published this information on the internet and it was grabbed by a large language model, well, it will be very difficult to erase it from there. Yeah, I do agree with that. So that's a risk, I would say, that if you once managed to publish this information and it was grabbed by ChatGPT or Gemini, it will be very difficult. But if you are able to, for example, if you are not talking about a public GPT engine, but I'm talking about an instance which I'm managing, I can put a filter. So when the large language model gives a response to my question, I can apply a filter before I send it back to the user, right? And this filter can filter out the sensible information. There are some flags of these APIs where you can set that which kind of information should be allowed. So for example, if you switch on a flag on this API that do not respond anything which is related to hate speech, for example, then the model will filter out all the generated answers which might be classified as hate speech, right? So this is similarity to grounding for a models what you have developed and you are using in your application, you can filter it. But for ChatGPT, you do not have really a control. So once it was grabbed your information, then this is in there somewhere. So if somebody will ask that question from ChatGPT, it might answer. However, as far as I know, these large vendors are also put some filters into these models. So for example, you cannot ask diagnosis based on an X-ray picture from Gemini because it will respond you that I'm not capable of doing this. And probably there are filters in these large models which are filtering out the personal information or those information which are classified as sensitive ones. But this is the service of the provider. Yeah.
Okay, that's a good answer. Thank you very much. So let's jump to the next one. You mentioned that the larger the model, the better the capabilities. However, this requires more resources and time. How can I choose which model to use? Is there any good resource that compares models of different sizes and gives guidance about what capabilities each size has or what tasks they are good at?
Yeah. So the answer is is very simple: experimenting, right? So there are no such database. So of course, for each model, so if you are searching for a model, you will find a data sheet, and that data sheet will include some information about the capabilities of the model and what it is trained for, and what is the data set which is used for the training. But at the end of the day, what you need to do is do a lot of experimenting, right? And ask questions. And if it's good, gives you a good question, that it seems to be that it can be properly used for that purpose. But so that's what I would suggest: do a lot of experiments. Yeah. And for the resources it consumes, so actually it is also something. So you saw my offline models, right? And when I asked the question, it responded very slowly. However, I was the only client of this large language model. And actually, this is also an experimental thing. So if you are satisfied with the response time, then the background infrastructure is big enough. If you are not satisfied, then you need to increase the size of the infrastructure. There are no, as far as I know, there are no explicit sizing documents for this kind of large language models, or at least I haven't seen any of these yet.
Okay, thank you. Let's jump to the next one regarding the vectorization and the 3D semantic feature space slide. So the diagram that depicts the 3D semantic feature space. So let's just have a question regarding this. How extreme cases are handled? For example, if we consider in the British royal family, a prince could be even more than 60 years old, or in other countries, a king could be very young, like 1 to 3 years old in some countries. And a related question is that how the context could be identified. So, for example, the queen as the queen of the country, and there is a band called Queen, and so both of them can have relations to each other. So the queen can have a relation to a prince in the royal family, but the queen, the band, can have a relation to Prince, the singer. So how are these like handled separately?
Yes, yes. Okay, these are very good questions. So first of all, this picture is just an example, right? So the dimensions will not be the same. So it will be, as I told you, it will be some random parameters of a trained neural network. So there we will not be able to identify that out of these 4,000 dimensions, what we are using for embedding a word, the first one is about age, right? So there is no such information because it's not made for that. So this was just an illustration of the thing. But the other thing is the other part of the question is really interesting. That okay, how you differentiate the band called Queen from Elizabeth, the Queen of England, right? And that is where, for example, these advanced models are used. So, for example, this model of transformer is used, which is able to understand these context differences. And what you can do is you use this transformer for classification, for embedding this environment, and use the hidden layers. So if we are looking at, so a transformer will be much more complicated than this neural network, but it will have a final neural output, and it will have parameters. And you can use these parameters. And in that case, if you are using a language model parameter, which is able to differentiate queen the band and queen the person, then the embeddings for the word queen will be different if you are searching for a queen the band or queen the person, right? So this is a little bit mystical thing, I would say, but it works, right? So if you are using this kind of large language models, they are able to, based on the query, what you are describing. So if you are a query, you are entering that I would like to get more information about the queen, the band, right? And both the queen and the word band will be next to each other, then it will understand that you are talking about the band and not about the person, right?
Okay, thank you. So let's just check one more because we are quite short in time. We have one from the chat. When you write disadvantage about offline model, resource requirement is hardly predictable. How does it look like in reality?
Yeah. So what you can see here, for example, in these VM instances, so this VM contains 70 gigabytes of memory, of RAM, and 200 gigabytes of storage. It has got 16 cores of CPU and a T4 GPU inside of that. And actually, it produces a quite slow response, right? So in reality, to execute such a large language model like Llama 3, you would need at least, I don't know, twice as big machine for a single client, right? And if you would like to have 100 simultaneous clients, then you need to have a much larger model. Of course, you need to experiment. What my experience is that memory is very important. It is probably the most important thing because you have to load all this neural network into the memory. And if you have more memory, it has a very good impact on performance. But the other parts like the GPUs should be scaled up if you have got more questions or more complex models. But it depends also on the models as well. Okay.
Okay, thank you very much. And the last question is a quite short one from the chat. What is a parameter? But I don't see the context exactly. I don't know if this could be answered.
So the parameter is the connection. So the weight, here you can see the neural network, right? And these weights, so some of the connections are thick, some of the connections are thin, and each one is represented by a number, right? And the parameter is this weight between two neurons, right? That is the called parameter. In large language models, you have got billions of these because you have got millions of neurons, and the parameters are also in a billion way. And this is what you save in the model when you would like to reuse it, right? So this is the word parameter means in the context of large language models.
Okay, thank you very much. That was the last question. I would like to say thank you for this brilliant presentation. It's always refreshing to see what happens under the hood, not just telling us that use AI because it solves everything. So it was a very useful information and a great presentation. Thank you very much. So let me hand over to Camilla to.
Thank you as well.
Thank you
for having me.
Of course. Thanks, everyone. And let me thank the audience for joining us. I hope you enjoyed today's session. And don't forget that the recording will be available on our YouTube channel, Clouders Club, in a few days, so you can rewatch it anytime. And if you're not a member yet, I suggest you click on the join button and become a member at GDG Cloud Budapest on meetup.com, so you will get notifications about future events on your private emails as well. That's it, I think. Thanks, everyone, again. Have a nice evening. Bye-bye.